Hi there, this is Walter Gilioli, and this is a quick recording of the final project for 413 time series forecasting, where we're really trying to predict disease spread of dengue. This is a disease caused by mosquitoes in some part of the world. I grew up in Guatemala, and I know this is a very common disease there, unfortunately, that has huge implications for safety. And just being able to predict and understand this would definitely save lives. So I would say the significance of doing something like this is very high. In terms of the data set, I'm just going to make this a bit bigger. In terms of the data set, there were two files that had to be merged together in order to have all the information in one data frame in R. Almost 1,500 observations and 25 variables. I won't describe all of them. I would just say that there were like 4 variables describing generals about, we have data for 2 cities, so that had to be addressed later, and then some information about the date. Then we had 21 numerical observations that included total cases, which was the variable we're going to predict, and then we have 20 potential predictors. So this is a very complex data set, and some things were addressed. Let me jump to this first. There were a lot of missing values for these numerical attributes, so I decided to keep it simple and do imputations. I didn't want to delete observations. I know R has a fancier package to deal with missing values, but I did it the good old way. Just check if there was a missing value, and if there was, I inputted the median for that particular variable across the board. Usually, I like to do something with outliers, especially or some transformations, but I decided not to do it. I just had to balance and prioritize, and I prefer to spend more time testing different modeling techniques for this particular case. So once I did the imputations, and again I didn't address the outliers, I usually pick and I trim at the 1%, 2%, maybe 98 and 98, 99%. So this is roughly the data that we have of all of this, which is around temperature, rain, things like that for that particular week. Once I did that, I had my data set. So what I did is I split the data set in two because we have 2 cities, and I wanted to handle that separately. So one for Iquitos and one for San Juan. And then the next thing I did was I had 2 data frames, so I converted that to time series objects. And I plotted this here just to get an idea of what I was seeing. And I'm still not an expert in identifying trends, cycles, white noise, all the things that we are learning in the course. But from what I can tell, it's pretty messy what we have here. So based on seeing this and seeing all this weekly data over time, I decided to test different techniques. And I'm going to talk about that next. I just want to quickly mention that I found very interesting cases online about articles published around using time series, for example, to understand climate change, to understand the prices of houses, and to try to predict the stock market. I'm still very skeptic about that, but it was interesting to see. So the links are there. In total, I ended up doing 5 models, and I'm showing all of those 5 there. I wanted to test different things, not spend a lot of time in one technique, but just make it work. And this was challenging because, for example, for it number 1 and number 2, I could simply use my time series objects and do very simple modeling with those. But for linear regression, for example, I had to use the data frames. And for dynamic regression, I had to use ARIMA, but then I had to build a matrix of the regressors and include that as a parameter. So it was very interesting to try all of those. And then I tried neural network autoregressions as well. So very different techniques. I decided not to spend a lot of time trying to tune the parameters and let R do the work for me, as we saw, for example, in John's presentation with the motorcycles. And needless to say, I'm amazed at the results that I found. I remember a good friend of mine that does data science at Microsoft told me, linear modeling is old, but it's usually very good, and it's usually all you need to know if you want to work in data science. And I was a little bit skeptical about that, but that it seems that there are fancier techniques. I took machine learning last quarter, and there's definitely things like Reach, Lasso that make it more complicated and fancier. But once I tested my models in driven data, as you can see in that table, linear regression is the one that performed the better. I didn't even have to split the data set in two for the two cities because I let that attribute to be one of the predictors as well. So that was easier to do than the other four models, which in essence I had to build two models, build two predictions, and then concatenate the results to produce the output file. A note I want to say here in performance, I took the easy way out. Usually, I probably should have split my train sets in train and validation, and then see some of the performance metric on the validation set, like RMSE. I decided not to do that because I understand that's what driven data is doing for us in this competition. So I saved some time doing that. Um, there's definitely other things to mention here, but I probably just want to highlight that one of the things I loved the most about this course was learning with time series and learning how complicated and how easy it can be to predict time series. I've never done it. I've just pretty much done the trend lines in Excel, and that's it. But now I feel like I'm very armed to do more serious series forecasting, and even offer to do some at work. Linear regression, again, keeps ruling, and we don't need to forget that simple sometimes is better. And I like doing competitions in driven data and Kaggle. I've done a few, but I probably will do more, and maybe even see if I can put it in my resume, if that helps me to land a job in data science. I hope this presentation was useful to all of you. Thank you very much.